All right, let's make this a little bit more complicated. So in complex reactions, we need to use oxidation numbers to identify which atoms are oxidized and which atoms are reduced within a compound. So again, if an atom's oxidation number increases, it's oxidized, and if an atom's oxidation number decreases, it's being reduced. The atoms whose oxidation numbers don't change are called spectators. So this is usually going to be your oxygens and your hydrogens, unless there's a diatomic oxygen or a diatomic hydrogen, or like a free oxygen or a free hydrogen is in the reaction. And you'll see what I mean as we go through some examples. So in this first one, we've got 3 species on the left and 3 species on the right. We have to try to find the compound that has an element in it which is being oxidized or reduced. So when we were talking about the hydrogens and the oxygens, when we look at something like the water going to this hydrogen ion, the hydrogen in water is a +1 because there's nothing, like it's not a metal hydride, and the hydrogen over here is also +1. So that's going to be one of those spectators whose oxidation number is not changing, so it's not being oxidized or reduced. So that then leaves us with SO2 going to SO4 2-, and then the ClO3- going to the chlorine ion. So what we're going to do is we're going to have to then go into these compounds and, without bolding, because hopefully you've done enough practice with this now, figure out which element within the compound is being oxidized or reduced, or which one's going to have a change in oxidation number. Now, it's normally going to be one of your group 1 metals, your group 2 metals, hydrogen, oxygen, or your halogens, although there are some exceptions as we learned with those. So let's look first of all in the SO2 going to SO4 2-. For me, I can look at this and be like, well, the oxygen in neither of these is a peroxide, although you might be seeing this O2 and thinking, wait a minute, O2 is peroxide. Not with sulfur. Sulfur is another non-metal. Non-metals don't form peroxides. So I'm going to guess that it's going to be the sulfur that is going to change its oxidation number. So I'm going to say that on the left-hand side, we have sulfur plus 2 oxygens equaling 0. It's the sulfur that I'm going to find the atomic number of, or the oxidation number. I'm going to say that each oxygen is -2. So sulfur on my reactants has an oxidation number of +4. For my products, again, I'm going to guess it's sulfur. I have 2 sulfurs and 4 oxygens, this time totaling -2. And again, I'm going to put the oxygens at -2 each because it's not a peroxide. So then I'm going to add 8 to both sides, and I get that this sulfur has an oxidation number of +6. This says that I'm going from +4 to +6. This is an increase in oxidation number. Increase in oxidation number means that this species has lost electrons. You would need to put 2 electrons over here to balance the charge. So I'm going to say that this is the species being oxidized. So SO2 is being oxidized, which means it's acting as the reducing agent. Now let's prove this to ourselves by checking out one other element and hoping that it is reduced. So now I'm going to choose the chlorine on the left and the right. Now on the right, chlorine has its normal charge of -1, but on the left I have chlorine with oxygen. And chlorine, or any halogen with an oxygen, can change its oxidation number to being positive. So on the left I have chlorine plus 3 oxygens equaling -1. The oxygen is not going to be anything different than -2. So then I'm going to add 6 to both sides, and I end up with chlorine having a +5. On the product side, I have chlorine to the -1, which means that its oxidation number of chlorine is -1. This is a decrease in oxidation number. In other words, the oxidation number is reducing, which means that chlorine in the ClO3-, so it's the chlorine that's changing its oxidation number, but it's that whole compound that's going to be considered as the being reduced, and the oxidizing agent as well. And again, for this one, I can think of the electrons belonging on the reactant side because I would have to add 6 electrons in order for it to be balanced in charge. Awesome. Okay. And if anybody's thinking of this now, I forgot to mention it before. The reason for the coefficients is because of the electrons. Like, see here how I said that we've lost 2 electrons, but this guy's gained 6. This 2 needs to be multiplied by 3 to make it 6 electrons. That's why this coefficient exists. So don't worry about the coefficients in your half reactions, but they are super important when we think about balancing an overall redox reaction, which we'll be doing in a few lessons. Okay, let's try this one. So for this one, again, we have to find the species that we think is going to be oxidized and which species is going to be reduced. When I look over here at the water, I'm probably not going to count it. So when you look at hydrogen on the left, you have this hydrogen like HNO3, this nitric acid, and the hydrogen is going to have a normal +1 charge, and so is it in the water. When you look at the oxygen, it's going to have a -2. Oxygen is going to have a -2 over here. So my guess is that it's going to be the sulfur and the nitrogen. So my 2 half reactions are going to be that sulfur goes to SO2, and then the HNO3 is going to go to NO, and again, just leave off the coefficients, and I'm going to look at the difference in the oxidation numbers of the sulfur and of the nitrogen. Feel free to pause the video and give this part a go if you're feeling confident. So for this one, the sulfur on the left has an oxidation number of 0. This is a free sulfur. And then in the products, we have sulfur plus 2 oxygens is equal to 0. We're going to assume that the oxygens have a normal -2 charge. Oh, I wrote a 2 instead of an S there, sorry. S plus 2 times the -2, which means it's going to have an oxidation number of +4. This is an increase in oxidation number, so it is going to be the species that is oxidized. The other thing I like to think of is that increase and oxidize both start with vowels, whereas decrease and reduced, decrease and reduce mean the same thing, plus they start with consonants. Whatever floats your boat. Over here, my reactant, we have a hydrogen plus a nitrogen plus 3 oxygens equal to 0. We're going to find the oxidation number on the nitrogen, so I'm going to consider the hydrogen a +1, and I'm going to consider each oxygen a -2. Find the exceptions come up very rarely. So I have nitrogen -5 is equal to 0, which gives me an oxidation number on nitrogen of +5. And on the right-hand side, I have nitrogen plus oxygen equal to 0. Again, I'm going to assume a -2 for the oxygen, which means my nitrogen is +2. This is a decrease in oxidation number, which means that this is the species being reduced. So the HNO3 is being reduced and acting as the oxidizing agent, whereas the sulfur was being oxidized and acting as the reducing agent. Now, usually they won't ask you for all 4, they'll ask you for like one of them, but it's good to know all of them. All right, I have one more example that's big like this, so I'd like you to pause the video and give this one a go. All right, so again, first thing you have to do is decide which elements can be oxidized and reduced. I often don't look at the oxygens and the hydrogens, so I'm going to like right away zone in on the chromium, and then I'm guessing the carbon as well, although we could be wrong. So one of my half reactions is the CrO4 2-, and it's going to go to the CrOH3, and then I'm going to guess the HCHO is going to go to the HCOO-. And again, I pretty much know to ignore oxygen and hydrogen because there are no free hydrogen and no free oxygen in the reaction. So now I'm going to go through and I'm going to find the oxidation number of chromium and then the oxidation number of the carbon. Okay, so for this one, chromium plus 4 oxygens equals -2. I'm going to put the oxidation number of oxygen as -2. So then the oxidation number of this chromium is +6. For this one, now again, you can do this as chromium and 3 oxygens and 3 hydrogens, Or you can do this as chromium and a hydroxide because we know the charge on hydroxide. It is kind of personal preference. If you're being kind of a perfectionist, you'll do chromium and 3 oxygens and 3 hydrogens is equal to 0, but it'll come out the same. So we've got 3 of the -2s, we've got 3 of the +1s, which is going to give you -6 + 3 is -3. And then you've got the charge on chromium being +3. And again, if I had done that as chromium and hydroxide, you'd have 3 hydroxides. And then we know the charge on each hydroxide is -1. So again, you would get chromium is equal to +3. It doesn't matter. But for this one, we've gone from +6 to +3. This is a decrease in oxidation number, which means that the chromium in the, I believe that's chromate, is being reduced. So CrO4 2- is being reduced and acting as the oxidizing agent. I have seen sometimes where they talk about the actual element being reduced, so it's like the chromium, you wouldn't put CrO4 2-, but I think our textbook, which is why I'm writing it this way here, does the whole thing. And then for this one, we're going to solve for carbon. So this is a carbon and 2 hydrogens and an oxygen equal to 0. So carbon and 2 +1s and a -2 is equal to 0. We end up with carbon +2 is equal to 0, and the oxidation number on carbon is -2. And then for this guy, we have a carbon, a hydrogen, and 2 oxygens equal to -1. Getting a hand cramp. So carbon plus that hydrogen is +1, plus each oxygen is -2 is equal to -1. That's going to give us carbon -3 is equal to -1, which would give me carbon of +2. And again, what we're looking at is that this is an increase in oxidation number, which means that the HCHO is oxidized and acting as the reducing agent. Great. So hopefully that was enough examples that you feel kind of confident in that. I didn't know if it was too much or too little, but the last part is just some different sorts of questions. So for the next one, it says, which of the following species could be produced by reducing Fe3+? If you are reducing Fe3+, you need a decrease. Oh dear. Having troubles with the word decrease. It is going to be a decrease in oxidation number, so something smaller than a +3. So the only one that could be the product of a reduction of Fe3+ would be Fe2+. Now we should check the FeO4 2-. I should pretend like I don't already know the answer to this. So this would be iron plus 4 oxygens is equal to -2. So it's going to be iron plus 4 of the -2 charge is equal to -2. Add 8 to both sides, and we end up with the oxidation number on this iron of +6. So it is not less than +3. So it cannot be the product of the reduction of Fe3+. Whereas in the second question, when it says which of the following species could be produced by oxidizing Fe3+, we want an increase in oxidation number, whereas this was a decrease in oxidation number. And there are 2 answers. 4 would be an increase in oxidation number, and this +6 of the FeO4 2- would also be an increase in oxidation number. Awesome. Go and try some questions like that in the textbook.